Start recording.
Decrease
Stop recording.
acidity.
Button.
So carbonic acid is a buffer. It minimizes extreme changes in the pH, and it keeps the pH level in your blood in balance. And you have an enzyme that does that. Remember enzymes with protein? It acts like a tool, puts things together, takes things apart. So you have an enzyme that drives it in the bloodstream. So that's a buffer. And that ends chapter 2, and so now we're in chapter 3. We've picked up, we're picking up that handout. Just that first page of the handout we're going to do. Now, this chapter is about molecules, large organic molecules. Carbon, or organic molecules, are molecules that are, have carbon in changing rings. So let's look at carbon for a minute. Let's do a review on some of these chemical bonds. We've got, well, I'll do it this way. If you grab chalk in your eraser, it just makes marks while you're trying to erase. Okay. All right. Remember hydrogen. Hydrogen has a single proton, so it has a single electron. So hydrogen can form a single covalent bond. Then we looked at carbon. We said carbon has 6 protons, so carbon has 6 electrons, and we put 1 in each of that hour. So carbon can form 4 covalent bonds. And then we looked at oxygen. Oxygen has 8 protons, so it has 8 electrons. And we put, so that leaves oxygen then able to form 2 covalent bonds. So when you fill those, remember how we filled that? You put 2 in that innermost, and then you put 1 electron in each orbital, and when you have 1 electron in each of the 4 orbitals, then you go back and put the second electron in the orbitals, so that you have a maximum of 8 electrons in that outer orbital. But oxygen only has 6, so where it leaves those two orbitals that only have 1 electron, that's where you can form a covalent bond, right? So you can put a covalent bond there, and a covalent bond there. Carbon has 4 electrons in its outer shell, and each of those electrons then can form a single covalent bond. Hydrogen only has 1 electron, so it only has the innermost, so it can only form a maximum of 2 electrons in that inner, so it can only form a single covalent bond. Now, I know we went over that in great gory detail, but just a review. You're going to need to know this for the rest of the semester. Everything we're going to do from now on, you're going to have to know the number of bonds. So you can just memorize hydrogen forms 1 covalent bond, carbon forms 4 covalent bonds, and oxygen forms 2 covalent bonds. Is that going to be a question on the test? Something like that, probably, yeah. Now, it may not be a test on later chapters, but you got to know it. So we have a test question this time, and then you know it for the next. Now, the thing about memorizing, you can just flat out memorize. Hydrogen 1, oxygen 2, carbon 4. You can just memorize. That's the number of covalent bonds. That'll get you through this semester. But if you understand why, then you've learned it, and now you can look at nitrogen or fluorine, and you can figure out how many covalent bonds that it forms if you understand why. So you've learned it if you understand why. if you memorize it, well, you've memorized it, you've got through the class, you're done, and you can go on with your life. But you haven't really learned it. My advice, you understand it, but memorizing that will get you through the semester. 1 covalent bond for hydrogen, 4 covalent bonds for carbon, and 2 covalent bonds for oxygen. Now, let's look at carbon, because we said organic is carbon in chains or rings. And remember, we'll look at oxygen too. So remember we said this, we can shorthand that and just put a C, and then we put 4 bars, and each one of those bars represents a single covalent bond. So the easiest thing to do is take hydrogen on. So we can put 4 hydrogen around that carbon, and that gave us methane. And we said methane is flammable. So when you see carbon and hydrogen bonds, think there's a lot of energy stored in covalent bonds. Now, all chemical bonds have energy stored in them. Some bonds are stronger than others. But the bonds that hold carbon and hydrogen together, carbon shares very evenly, and so it doesn't take a lot of energy to break these off. So those are good energy molecules. It's like that business investment. You put $50 in, you get $500 out. That's your carbon-hydrogen bonds. If we look at oxygen, one of the things we do with oxygen is we made a polar molecule, because oxygen is an electron thief, it steals electrons, and we made 2 single covalent bonds with hydrogen and made water molecules. But we also, remember in lab, we made carbon dioxide molecules. Because carbon can form 4 covalent bonds, and oxygen can form 2 covalent bonds, it can form that double covalent bond. Now, double covalent bonds are pretty common. Triple covalent bonds are very rare, and there's no such thing as a quadruple. You don't get 4 covalent bonds. Water, carbon dioxide. Oxygen will double bond to another oxygen. So you think oxygen gas, there's oxygen floating in the air around you. That's generally going to be oxygen gas. It's 2 oxygens double covalently bonded to each other. Now remember we said that ozone, you put a third oxygen, because it's up there in high in the atmosphere where the UV light's burning down on it, and it makes, it gives the radiation, so excess energy, and it does wonky things it's not supposed to do. That's why radiation causes cancer, because it damages your DNA. So we can so that's where that third oxygen gets stuck on there, and that's ozone. That ozone layer is 3 oxygen molecules bonded together. So see how that's kind of weird? That's weird. We can make bacteria for that. Hang on. So those are, now, those are all single covalent bonds. Now, a long time ago, the definition for organic was carbon in chains or rings. These are single covalent bonds. They didn't have a carbon in it. That's just got a single carbon, that's just got a single carbon. We only got 1 carbon. It takes 2 to make a chain, right? A minimum of 2 to make a chain. Probably 3 to make a ring. You can't really make a ring out of 2. You take 3 together, and that kind of makes a triangle, a 3-sided ring. But here we've only got carbon and water and methane. Bacteria produce methane. sources. We find methane and carbon in water, we find those in living organisms, right? Well, water's not gonna be an organic molecule, because it doesn't have carbon at all in it, but some of these others are small, like carbon dioxide, is in your bloodstream, methane is produced by bacteria. They don't have carbon in chain rings, but they are produced by living organisms, so the old definition was molecules that are produced by living organisms, but this guy named Stanley Miller came along and he did some experiments with some flask, and he put some water and some carbon dioxide and a few other things, and he put some heat on it, and he put some coals around, and had 2 or 3 of these things set up. It's a little elaborate. He was demonstrating or trying to see if you could get organic molecules from an inorganic source, from a non-living source. So if you just got water and carbon dioxide and a couple other little things, can they be spontaneously put together? And he found, yeah, they can. So there was he's always cited for evidence for evolution of the organic molecules forming in this ooze, and then the molecules coalescing, and then cells being produced. Still haven't explained though how they became alive from inorganic dead, but whatever. That's one of those areas where scientists think they not all scientists. Because scientists know, the more they answer a question, the more they ask why, the more questions they have. Every time they answer a question for a scientist, they have more questions. But somehow there seems to be this, oh, well, you know, there's the Big Bang, and then there were these single cells, and now there are multi-cells, and that's evolution, and that's how we got here. You still haven't answered the question of how it became alive. What is, you know, it's alive. It's not just a clump of molecules. Anyway, changer rings. So Stanley Miller was able to produce some very simple organic molecules from inorganic sources, and so they kind of changed the definition of organic molecule from produced by living organisms to carbon in chains or rings. However, carbon dioxide and methane are produced by living organisms, so small, simple molecules like that are still considered organic because they are produced by living organisms in that same, even though you can't form a chain or a ring. So how do we form chains or rings? Well, let's look at carbon. We got these covalent bonds going on here. We'll just let's do 4. 1, 2, 3, 4. And if we just go ahead and stick hydrogen on there, it's not methane anymore, now it's butane, which is still flammable, right? Carbon, hydrogen bonds, that's gonna be flammable. Butane flammable. Butane lighter. Y'all ever heard of a butane lighter? Okay. How many of you have ever used a rotary phone? One. We had one phone and it was in the kitchen, it was rotary. We missed phone calls, might be 2 or 3 days before we found out who it was that called. And we had a party line. If they were on the phone, we couldn't use the phone. So, good old days had their problems just like today does, but anyway, that's butane. Butane's flammable. So carbon, hydrogen bonds, energy. Pure carbon, hydrogen bonds and nothing else, potential to be flammable. And that's a chain. We've got 4 now, so we can make a chain. So there's a chain. Butane is considered an organic molecule. You can take organic chemistry. I don't know if it's offered here, Jeff State, maybe I'll look. You're saying no, it's not. Somebody in my other class said it is. I don't know. Chemistry is offered, but not organic. So you have to go somewhere else to get an organic chemistry class. Organic chemistry is going to be the chemistry of this chapter. Chapter 3, but you go and you look at it from a chemistry instead of a biological standpoint. Now let's make a chain in the ring, because that's a chain, it's not a ring. If we put and I'm making up a molecule now. You get some example. Okay, so that's sort of squarish. Let's move these up. You can see that if we kind of spread it out a little bit, you're getting chains. And remember that carbon's going to form 4 covalent bonds. So I'm going to stick an OH over here just because. And these, let's make this. Put some double bonds there. All right, now let's look around. Let's count some of these bonds around this carbon, because sometimes they do this. They've shown here. We've got. So this carbon has 1, 2, 3, 4 covalent bonds. This one we got 1, 2, 3. So sometimes they just leave off because you know that carbon forms 4 covalent bonds. So rather than write it, just go, okay, here's carbon 1, 2, 3, 4. You just know that there's another hydrogen there. They don't draw it. You just know it. 1, 2, 3, 4. So you have it here. This one we've got 2 hydrogens. So this carbon has 1, 2, 3, 4 covalent bonds. This one has 1, 2, 3, 4. We could put another hydrogen there. We could put an OH here. So there's 1, 2, 3, 4, 1, 2, 3, 4. This one has 1, 2, 3, 4. So all of our carbons now have 4 covalent bonds. Now, I made up this molecule. I don't know what it is. It doesn't matter what it is. It's the characteristics for this molecule that we're interested in looking at right now. When you've got these single covalent bonds, remember from our lab, you got a single covalent bond that you can twist them, you can turn them. That's a single covalent bond, so it's like, so here's a single covalent bond, and these can be twisted, right? I can twist around. But if I put 2 covalent bonds together, I can jiggle a little bit, but you can't spin it all the way around. That lends shape then to this molecule. We can spin here, this carbon at the top, but these single covalent bonds can kind of spin. But these double covalent bonds, we put 1, 2, 3, 3 sets of double covalent bonds on this ring of carbon at the bottom, that can't spin. So this OH here is going to stay right there. It's not going to move. We got 1, 2, 3, 4. This OH can spin around, but this carbon cannot spin. Now we got a double bonded oxygen up here. That can spin around, and as that spins, it's going to change a little bit of shape of that molecule. Change the shape of the molecule, you got to use a different enzyme. Because remember, enzymes are a protein, they act kind of like a tool, like a screwdriver. You can put things together, you can take things apart, but like a screwdriver, it's got to have the right size, it's got to have the right shape. So double covalent bonds versus single covalent bonds is going to give properties to that molecule. When we say the properties of that molecule, what it will and won't do, what other molecules it will react with, like if it's polar or non-polar, if it's got single covalent bonds or double covalent bonds, it can spin, the shape can shift a little bit. One can have one shape, one can have another shape. So those are the properties, and it's gonna react with different organisms, but other molecules that has different properties. So, if you get a loop of a ring of carbons, so you saw a chain, butane was a chain, four carbons with a bunch of hydrogens on it. Now we've got a ring of carbons. So there's our organic molecules. And a little bit of the characteristics for those covalent bonds. Because we're gonna look at a few molecules, and you ought to be able to look at them pretty quick, go, oh, well, that double covalent bond is not gonna spin, this one will, there's an OH on there, and an OH can break off and give us an acidic quality. Now, our organic molecule, we've got 4 organic molecules. If we take you apart, now of course you got carbon dioxide, you got water and other small molecules, but the big molecules that make up your body. We can take the large molecules that make up your body, and they're gonna fit into one of these four groups. Carbohydrates, proteins, nucleic acids, and lipids. So carbohydrates, proteins, nucleic acids, and lipids. Pretty much we can take your body apart and take the large molecules and divvy them up into these 4 groups. So all living organisms are composed of these 4 groups of large organic molecules. Macromolecules. Microscope, micro with an I means small. Macro with an A is the opposite, it means large. So these are macromolecules with an A, large organic molecules. Carbohydrates, proteins, nucleic acids, and lipids. And this is the order we're going to do them in. Because carbohydrates, we'll do that today. Monday, we'll do protein, and then nucleic acids and lipids. We can finish those up pretty quick. And from lipids, we move straight into chapter 4, which gives us plasma membranes of cells. So, chapter 4, we start talking about cells. Finally, we're going to be talking about something that this is supposed to be a biology class, and so far all we've done is chemistry. Well, living organisms are chemistry factories. You got to understand some basic chemistry to understand photosynthesis. So, carbohydrates, proteins, nucleic acids, lipids. We're going to do carbohydrates today. We'll do proteins on Monday. That's probably where we'll end the test, and we'll introduce nucleic acids and lipids, and that'll be on exam 2. So, carbohydrates. Carbohydrates have their organic molecules that have carbon in chains or rings. So on your paper there, you've got 2 of them drawn. Well, okay. So to define a carbohydrate is going to have, there's the glucose and fructose. Those are on that handout. We're going to look at those in just a minute. The carbohydrates are going to have this molecular formula. And what a molecular formula is basically, it's the recipe. You can take flour, buttermilk, and eggs. You make biscuits. You make pancakes. So you got a recipe, you got a list of ingredients, but it's how you put those ingredients together is what you're gonna make. So this is the molecular formula. We've got a carbon, and then in the same number, we got the same number of carbon and the same number of oxygen, but for either of those, we got twice that for hydrogen. In other words, you can say for every carbon, there's a hydrogen, and for every oxygen, there's a hydrogen in the sum total. So we can, simple, we multiply through it. This is, simple algebra. We were doing this in what, 4th, 5th grade probably? You can divide through. Now remember, when there's not a number with this little superscript with that carbon, it's understood to be 1. So 3 times 1 is 3. So that's 3 carbon, and then 3 times 2 is 6, so there's 6 hydrogens, and 3 times 1 on that oxygen is 3 oxygens. So C3H6O3 would be the molecular formula for this organic molecule, this simple carbohydrate. We can do it with 5. So we go 5 times 1 is 5, 5 times 2 is 10, and then 5 times 1 is 5. I almost put that too big, smaller. So C5H10O5. So you see we've got the same number of oxygen and the same number of carbon, but there's twice that many hydrogens there. We can do it again with 6. So C6H12O6. Anytime we multiply through, we get a molecule and we can divide it out and we see we got the same number of carbon and oxygens, but twice that many hydrogens, then it's a carbohydrate. That's what makes it a carbohydrate. It's got that ratio of ingredients. Single carbon, oxygen, and then H2. That makes it a carbohydrate. So there's lots of molecules that fall into this category. And two we want to look at right now are glucose and fructose. So let's look at glucose. Glucose is C6H12O6, and that's what you've got drawn on the page there. You have glucose on the page. Let's look at this drawing on the page. No. I got one. Anybody else not get one? Now, this is just the handout for today's. I didn't bring. I had 2 on the weekend. I had fun and I didn't do all my work like I was supposed to. I've got, for you guys who just got the 1 page, I have got the full handout with all of them. They're at home. I only asked, because I had a bunch left over from last semester. So I have the bunch I have left over from last semester, so I'm gonna bring those in. I forgot to put them in our book bag. And I just got so I had enough printed with the ones that I have at home. We haven't plenty for class, but I left those at home, so, okay. Anyway, you got page 1, that's what you need today. We'll get you the rest of it next week. Don't worry about it, it's cool. So on that page, you've got this drawing, and there's a glucose molecule. And it looks something like this. Now what they have, first of all, we've abbreviated that chain, that ring. So if we had, we'll do 5. If we have 5 carbons, we know this is an organic molecule, so why don't we keep rewriting carbon all the time? Carbon, 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 carbon. We'll just leave the carbon off. So what we do is we take and draw this shape. This looks like the outline of a house, like you draw a house when you're a little kid. That shape. So you've got the peak of the house, that's where a carbon would be, and then the corner of each roof line, there would be a carbon there, and then at the floor, the basement, the bottom of the house, there's the other carbons. So everywhere there's a corner, that corner represents a carbon. So when we look at this drawing on the page, each one of these corners represents a carbon. There's a carbon there. We're just not drawing it because carbon, 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 carbon. Okay, so here at this corner, there's an O, there's an oxygen. So where there's not a carbon, it's designated as such. Could be a nitrogen. A nitrogen is another thing that you could stick in that ring instead of an oxygen. nitrogen can form 3 covalent bonds. Now, they also have some OHs. So let's look at those OHs. At this first one, that carbon forms 4 covalent bonds, right? Carbon forms 4 covalent bonds. But here for this carbon, we only see 1, 2, 3 that are drawn onto the page. Because we know there's the other hydrogens on there. So you know what's on there. We can finish filling it in. Here's a carbon. There's 1, 2, 3. So there's another hydrogen there. Here's 1, 1, 2, 3. So here's another hydrogen here. There's 1, 2, 3. There's another hydrogen there. And then at the top, there's this CH. Maurice, yours doesn't look like this because I've already drawn yours in for you. There's a C, a H2, and an OH, and it looks like this carbon and that oxygen, the way they have it drawn, it looks like that's a covalent bond there. Think about it for a minute. How many covalent bonds does oxygen form? 2. If this were covalently bonded, well, that's 1, 2, 3, but that says H2, so is that 4? Oxygen can't form 3 or 4 covalent bonds, so that can't quite be right. And that leaves this carbon out here only forming 1 covalent bond, and this hydrogen is forming at least 2, if not 3 covalent bonds. Something weird's going on there. So the way they have this drawn, they just put the molecular formula there, and it coincidentally happens to be stuck where it looks like that oxygen is covalently bonded to that carbon. We have to decipher this. What do we know about these molecules? Well, carbon forms 4 covalent bonds. So it's going to form the most, and we got to stick all these others on there. So let's do, and this is what I have drawn on yours, Maurice. There's the carbon covalently bonded to the carbon, and then that leaves the 4 covalent bonds. So we've got an OH at the top, and then H2 on either side. So there's the H2, there's the OH, and there's the carbon. So it really has this shape. But they drew it as a shorthand, just put the molecular formula in there. And that's fine. That's fine. It's okay to do that, as long as everybody knows that's what we did. Which, you know, when you get finished with class today, you'll know that's what they did. So, glucose has this shape. All right. Okay, this carbon, there's 1, 2, 3. We gotta stick another hydrogen out. Now we can count. Now we've got everything drawn in. Let's count and see if we got C6H12O6. So the oxygen, there's 1, 2, 3, 4, 5, 6 oxygen. So we've got O6. Let's count the carbons. 1, 2, 3, 4, 5, 6 carbons. So we're looking good. It's looking like a carbohydrate. It's got the right number of oxygen and the right number of carbon. Let's be sure, because that's 6. 6 carbon and 6 oxygen, so it should have 12 hydrogen, right? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, that's carbohydrate. Same number of carbon and oxygen, so there's 6 carbons, so there's 6 oxygen. That's the same number, and then you double that number. That's how many hydrogens we got. So it fits our definition of carbohydrate. So yes, indeed, glucose is a carbohydrate. So this is glucose, C6H12O6. Now you also have fructose on the page. looks a lot like glucose, and if we start putting it all together, it's got that house kind of structure to it, and then it's got, that, C H2OH. Yeah, right. That CH2OH, that's on there twice. So we made the ring a little smaller. We got 1, 2, 3, 4 carbons in the ring, and we've got 2 carbons bonded outside the ring. Here we've got 5 carbons in the ring and 1 carbon that's bonded like an antenna to the outside of the ring. Still C6H12O6. If I fill in this fructose the same way I filled in everything on that glucose, we could count out and we would come up again with the C6H12O6. But this is fructose. So fructose has C6H12O6. Glucose has C6H12O6. They both have 6 carbons, they both have 6 oxygens, and they both have 12 hydrogen. So when you just draw the molecular formula C6H12O6, which one are you talking about? Glucose or fructose? No. If all you see is C6H12O6, you don't know. Now, okay. Here's an end. Here's your clue. This is introductory biology, and all living cells utilize glucose. Bacteria, fungi, plants, animals, fish, you use glucose. On a cellular level, your cells use glucose. All living cells use glucose. This is introductory biology. So if you see C6H12O6, 99.9% of the time, they're going to be talking about glucose. So if you see C6H12O6 in your textbook somewhere, they're talking about glucose. Now, but fructose is in fruit. That's the simple sugar that's found in fruit. Glucose is in everything. Glucose and fructose have the same molecular formula. They're made out of the same parts, but they have a different shape. Molecules that have the same molecular formula but have a different shape are called isomers. Isomer. Remember we did isotopes? We said an isotope is the same atom, but it has a different number of neutrons. So carbon-14 is a radioactive isotope. Iso is the same, so it's the same atom, but different number of neutrons. So an isomer has the same parts. Same, and then mer means parts. So C6H12O6, that's the parts, that's its molecular formula, but they have different shapes, and so they have different properties. So it takes different enzymes to make them, to build them, and it takes different enzymes to break them down. The enzyme that you produce that will break down, digest glucose is not the same enzyme you use to break down fructose. It's a little different because they're different shapes. Remember, an enzyme it's a tool, like a screwdriver. Shape matters, size matters. It's going to put things together. It's going to take things apart to be used over and over again. So these are isomers. Another isomer that I'm not gonna give you the shape of because we start to get bogged down in what different shapes are. You see, this has a shape, fructose has one shape, glucose has another shape, they have different shapes. Galactose is another, C6H12O6, but it's an isomer. It also has a shape that's a little different than fructose and glucose. But it's still C6H12O6. So those are isomers. Simple sugars. They're also monomers or monosaccharides. Monosaccharide. Mono means how many? What's saccharine mean? What's this sound like?
Sugar.
Yeah, means sugar. The word for sugar actually is a very ancient word, and it's very similar in a lot of languages. So you get a lot of like sucker, like you're gonna suck on a sucker. They're not just called suckers because you suck on them. They're also called sucker because it's that sugar, that derivative of the name sugar. So a lot like a lollipop, the sucker. But sucker, sucker is an old, and it's spelled different. And it's like S-U-C-C-O-R, sucker. It means to nurture, but it comes from the old word of sugar. Anyway, so saccharine is sugar. So these are single sugar. So glucose, fructose, galactose are single sugars. They're monosaccharides. Now, more generically, they're monomers, which means one part. It's a part. More specifically, you say, this is a one part molecule that's a sugar. Then when you say monosaccharide, that's a sugar. But if I say a monomer, I might be talking about a nucleic acid. I might be talking about a protein. I might be talking about a carbohydrate. If I say it's a monomer. See, monomer is the generic word. Mono means one, mer means part, so one part. Monosaccharide is sugar. Now, that's versus polysaccharide at the bottom of the page. You got these two chains at the bottom of the page. You got the top one is starch, and the bottom one is cellulose. Those are both chains made up of glucose molecules. So poly means many. So polysaccharide, cellulose or starch are examples of polysaccharides. But a polymer might be, again, that's the more generic. We might be talking about proteins. We might be talking about nucleic acids if we're talking about polymers. You didn't know you could have typos right on the chalkboard. So those are words. So you got monomers and polymers. That's a more broad, more generic name, like tissue. Tissue is the generic word. Kleenex is the specific brand, and we call Scott tissue Kleenex. Got Kleenex? Coke. That's the. Hey, how you doing? You want a Coke? Yeah, what you got? Well, I got Sprite and Pepsi. Now, if you talk to somebody outside the Southeast and if you ask them if they want a Coke, they mean they want Coca-Cola. They don't want Mountain Dew or Pepsi or Sprite or Fanta grape, they mean, when they say Coke, they mean Coca-Cola. When we say Coke, it's any of those soft drinks is a Coke, Okay. They say pop, soda. But I think just about everywhere in the United States, if you say soft drink, you know that's a soft drink as opposed to a hard beverage like alcohol. Anyway, I don't even know what I'm talking about anymore. So, glucose, fructose, and galactose are saccharides, or monosaccharides. You put a chain of monosaccharides together, you get a polysaccharide like starch. Starch is a long chain of glucose. You can have 50, 100 glucose molecules chained together, and that will be a starch molecule. Where do you find starch molecules? Did you eat any starch molecules this week? I know you have because you live in Alabama. You've either had potatoes fixed some kind of way, or you've had some kind of noodles, macaroni and cheese. The only place in the world I know that macaroni and cheese is a vegetable. Macaroni and cheese is not a vegetable. But anyway, those have a lot of starch in them. Plants store energy in the form of starch. Glucose is a very stable molecule. You put a jar of glucose on the shelf, you come back 100 years from now, and you still got a jar of glucose. It's a very stable molecule. So you put a long chain of them together and you make starch. It's still stable because it's glucose, but it's also stable because it's starch, and so it makes a nice, easy molecule for plants to manufacture to store energy. You store energy as fat. Plants store energy as starch. And so starch is a carbohydrate. It's a long chain of glucose. It's a polysaccharide. But before we can build polysaccharide, so there you go. We got monosaccharides and polysaccharides. Let's look at some smaller disaccharides, some more simple. This is disaccharide. Di means two. So small saccharides, like a disaccharide, if we link, I'm not going to draw them out here, but we're going to link glucose. Glucose is one, and if we link glucose with fructose, we link glucose and fructose together, we get sucrose. Did you have any sucrose on your grits this morning? Or in your coffee? Or in your soft drink? You may not have. I did. I put sugar in my coffee. Sucrose is table sugar. Sucrose is a disaccharide. It's composed of a glucose molecule and a fructose molecule bonded together. And they make the disaccharide sucrose. Another example of a disaccharide is lactose. Lactose is composed of glucose and galactose. If you link together a glucose molecule and a galactose molecule, you get lactose. Any idea where you might find lactose? I know y'all all know this. Milk. Yeah, because y'all know people, you either are, or you know somebody, or you've heard of somebody that's lactose intolerant. They cannot drink milk. Milk upsets their stomach. Because, let's think about milk. What happens with milk? Who gets milk? Why is milk made, and who is milk made for? Specifically, not humans. Animals. Birds. Do birds make milk? Fish. Fungi. Plants. Oh, wait, there's a milkweed. Yeah, but that's not milk. It's more like latex. Y'all heard of milkweed? The sap in the milkweed is real thick, and it's very gluey, and so if you tear open a milkweed, it's real thick. Well, it's got some toxins in it as well. So when caterpillars or animals try to eat a milkweed, that tastes bad. And if you're like a caterpillar, it'll actually gump up your mouth. And yeah, a mouthful of glue, yuck. So it's a defense mechanism that milkweed have. That's not milk though. So who has milk? Cows have milk. What are cows? What about dogs? Kangaroos? Elephants? So what's the word for that whole group of? That we are? Yeah, mammals. Mammals make milk. Mammals are called mammals because they have mammary glands, and mammary glands make milk. Who's the milk made for? Your babies. Yeah. Mother mammals feed milk to their babies. Now, once a cow is weaned, the calf is weaned from its mother, does it ever have milk again for the rest of its life? What about a polar bear? Kangaroo? Zebra? Dolphin? Whale? Bat? Once mammals are weaned from their mother, they don't ever have milk anymore. They never have that in their diet. Except humans. So we'll get to humans in a minute. Now, it takes resources and it takes energy to produce the enzyme lactase. Lactase is the enzyme that breaks down milk. To produce the enzyme lactase, that requires resources and it requires energy. But as an adult, you're never going to have milk again for the rest of your life, so why waste time and energy producing lactase? You're never going to have it again. You're not going to use it anymore. So, okay. Do you have hair growing on your tongue? On your spleen? In your stomach? Now, all of the genes for how to make you are found in all of your cells, right? So every single cell in your body has the gene for how to make hair. But all of your cells do not make hair. Your cells become specialized for their one job. So you have hair on your head and other various places that are specialized to manufacture hair. All the other cells then, like your nerve cells, your muscle cells, they turn that gene off. They're like a cap, basically. It's kind of a cap. So it's a protein cap that you can permanently affix to your DNA that covers up that gene, so you can't read that gene. You can't use that gene anymore. So all of your cells have the gene for how to make hair is turned off in all of your genes, except where you make hair. Same thing for digestive enzymes. You don't want hydrochloric acid being emptied out into your ear, do you? But you manufacture hydrochloric acid for digestion in your stomach. So, now this thermostat does it, but I know y'all have seen thermostats that have the plastic case on them where they're locked up and you can't get to them. Only the maintenance person with the key can unlock them. Okay, it's kind of like that. You gotta think of that top cap adhering to and locking up your DNA so that gene is turned off. Now, because it's a protein, so we have this gene here that makes lactase. This is our lactase gene. But over here we have the gene that makes the cap to turn off the lactase gene. In mammals, this gene then, at the time it's weaned, so if you're an elephant, elephants take milk from their mom for a couple of years. Squirrels, weaned at about 9 weeks, puppies weaned at about 6 weeks. So it depends on what species you are at that age for your species. When you hit that age, when you're weaned from your mother, this gene that says, okay, we're at that age, it manufactures the protein and shuts down this lactose gene. Save you time and resources. You're not ever going to make any more lactose gene with you. Okay. All right. Now, what happened in human evolution is because there was in parts of middle and southern Africa, and then parts of Europe, and they had domesticated cattle. Now, in middle Africa and maybe parts of they had droughts. And if you had domesticated cattle, when there was a drought, you had milk to drink. So not only was it nutritious for the milk, but it also had liquid, had some water in it, and helped you survive the drought better. So if you can survive a drought longer than somebody else, then your descendants, you're going to have more kids, they're going to live longer, and they're going to have that mutated gene, because what happened is this gene over here that's supposed to shut off the production of lactase, this gene that's over here is broken. And it never turned off the gene, the lactase gene was never turned off. So the mutation isn't the lactase gene, it's another gene. This other gene is broken, it's mutated, and so you continue to produce lactase in an adult, and now there's a drought, and now you're drinking milk, and you've survived the drought longer, you have more. So for a mutation to be beneficial, to be passed along in future generations, it's got to have some kind of benefit. The benefit in Europe, Northern Europe, is it gets cold and frozen in the wintertime, and there's ice and snow on the ground, and there's nothing to eat. But if you are lactose tolerant, if you have that broken gene, you survive winters better. You've got milk that you can drink, cheese can be manufactured. There's cheeses throughout Africa as well. You got cheese and milk products that you can eat throughout the winter, and so you survive the winter better because you have an additional food source now. So see, there's that advantage. So when we see people that are lactose tolerant, generally their ancestry can be traced to Africa or Europe, generally. We don't see that mutation in people of Asian descent. Now this is this big, broad, general where your ancestors from. Here in the United States, our ancestors are from somewhere on planet Earth. Y'all all know, we all trace all our ancestry. The further back you go, we're from everywhere. Okay. I've got aliens pop. I got this headache right here. I think it's messing up my brain today. It's right there. Oh, it's out now. It's kind of like pounding. So, okay. Being beneficial. We still produce lactase. That's why you don't see, that's why you don't see cheese and dairy products in Asian cooking. Traditionally, I know we do it more here in the United States. We start putting cheese in Asian type meals, but traditional Thai, Japanese, Chinese, Mandarin cooking, they don't have cheese and dairy products in their traditional food. Because we don't see that gene in that part of the world, that mutation. All right, I'll see y'all Monday.
Stop camera. Stop recording.